Here we are, we have arrived at Space-Comm Expo 2025 and we're going to be racing around the exhibition, lots of face-to-face interviews, and we're going to be aligning all of the technologies and products on display with sustainable engineering's pillars of sustainable design. We're going to be looking for things that have been minimized, things that have been weight reduced, things that have been designed for reliability and durability, longevity, even things that are maintainable in orbit potentially by automated facilities. Anything and everything to keep space equipment and hardware as reliable and in service as long as possible. Right, we are on the Omnetics Connector Corporation stand at Space-Comm Expo 2025. And we're having a look at some of the interconnect technology that's on display today. And here we have a what we would call a hybrid or integrated nano connector with micro integrated into the device for power. So we're looking there at both signal and power integrated into the same device. Now that gives us an integration benefit, which comes with a weight reduction benefit. It's engineered for space environments, so we're looking at reliability, durability, standardized for shock and vibration for the launch phase, and then reliability and durability in orbit to keep the products alive and working as long as possible. And due to derating of power in space applications, these are sized for that specific environment for power and signal combined into the same device. So there it is. Great example of some space technology. Right, we're on the silicon sensing stand at the moment, and we're having a look at space grade sensors basically. We'll see gyroscopes and accelerometers so that spacecraft know where they are in space. Which is often a difficult environment to know where is up and where is down. And what we're looking at here are MEMS devices, micro mechanical sensing units. And really the benefit of these obviously is their durability and size reduction and weight reduction compared with more traditional gyroscopic units. Also shock and vibration resistant for launch phase, and then durable and reliable in operation in the actual space and orbit environment itself. So we can see here a whole range of technologies. We've already had a little look through the microscope. I don't know whether you can see that, but that's a Dcubed MEMS sensor in there, showing the wire bonding at the ship scale onto the actual gyroscope MEMS device itself, and then how that's packaged. So there we are, sensing in space on the silicon sensing stand. I'm here now on the Physical Mind London stand, and we're looking at some fascinating technology for exercising in orbit. So what we have here is the Hi-Fi-M, which stands for High Frequency Impulse in Microgravity. And this is an exercise unit designed to allow astronauts in orbit to maintain their bone density and their muscle mass. As a runner myself, I know how important exercise is to maintaining bone density and muscle strength and muscle mass. And the design of this particular machine is designed to provide a whole variety of exercise types, as you can see on the posters here. And in particular, one exercise which is jumping, which is the most important thing that an astronaut can do in space in terms of exercise, really important for the skeletal structure. And here you can see an astronaut jumping on the unit. It's manufactured from space-grade aluminium to keep the weight down, but most importantly, because of the variety of exercises you can do on this, it replaces multiple exercise machines that are on the space station at the moment. So we may well be looking here at the future of exercise in space. We're here on the IT Done Right stand, and we're with Greg, and we're going to be taking a look at the product, which is build intelligence technology. So, Craig, quick question for you, which is, what problem would a manufacturing company be facing for this software to be the solution?
Yeah, that is a great question. So it's all to do with the volume and kind of manufacturing they're doing. So for example, somebody building wiper motors, this wouldn't help them because it's high volume. But somebody where the work entails a lot of skilled hours, like from electrical engineers, mechanical engineers, all that kind of thing. This is where that will help because it helps with non-automated production and manufacturing.
Can you talk me through a classic application of where this would be beneficial? So talk me through a kind of workflow, where this would drop in and how it would benefit. And I think earlier on you were also mentioning that there's some AI integration in here.
Right.
If you can just give us a sort of summary as to the role that that's playing.
Absolutely, yeah, thank you. So a typical application might be satellites, aircraft or ships. So we're talking about something that's what we call low velocity, meaning the production is not an overnight thing. And the other area is high value. And so we're dealing with, when we're dealing with satellites, aircrafts and ships, all those criteria are true. And so that becomes a typical high value item to work on. And where it slots in is during the whole production cycle. In the satellite industry, we call it AIT, Assembly, Integration and Test. And so you've got your various components manufactured, like, regulators, solar arrays and so on, but you have to bring them all together in that production process. And that's where this helps, because it catches a whole plethora of issues that normally either don't get captured or just get stuffed in a spreadsheet somewhere and something like that. And what this does is it integrates all of that into one central area where it can analyze it. And we also work with AI in this area, but what we do is we bring AI to the table as a team member rather than the team leader. And we greatly value AI, but we've got to have facts. If you're building a nuclear missile, you can't be 98% correct. It has to be spot on. And so we use build intelligence for the facts, but we use AI for trends, for process improvements, pattern recognition, all that kind of thing.
We are here on the Dcubed stand, an organisation that specialises in the design of actuators for space environments. And what we're looking at here is a linear actuator device, lightweight, durable, reliable, engineered for space environments, for orbit environments. And this particular type of actuator would be used, for example, for the deployment of antenna and solar array. So what I'm going to do now, we've got a battery pack here, and I'm going to ask Dcubed representative Maria to power this up so we can see how it works. So, and there we go. Very powerful shutdown. And the good thing about this is that it is resettable. So there's a unit here which can be used in the rear of the device. I'll see if I can do it myself. So that device can now be reset and re-triggered. So reusable, no waste, not single shot device. There it is, actuator technologies for space environments. Minimization, weight reduction, reliability, reuse, very sustainable solution. Right, we are on the CRP Technology stand, and for all of those people that have read the latest issue of SE magazine, you will see the device on the cover here, and it is this product just here, which is an enclosure for space hardware. And this particular company produces a brand of additive manufacturing materials called Winform, and this uses selective laser sintering, SLS technology, to manufacture robust, durable, but most importantly, lightweight, complex structures. This is a polyamide material reinforced with carbon fiber. So this is advanced additive manufacturing technology here on the stand today. Now here's some other examples. See the complexity of some of these mouldings. Wonderful. So I'm now on the Space Whale stand, and as you can see from the poster, we're looking at some technology from engineering at Swansea University. And in the cabinet here, what's interesting is I am obviously a fan of additive manufacturing and 3D print. I run my own little 3D print cell at home for prototyping and product tests, that sort of thing. But what we're looking at here is a level up on my technology. So here we're looking at a heat exchanger for space systems. You see that lovely detailed matrix there. I would really like to be able to make heat exchangers like that. And then in the center, we've got some, let's have a look, that's Invar alloy for satellite components. Then again, back onto heat exchangers as we go to the left. Now they're lattice cube heat exchangers. Again, delightful structure of those particular products there. And then, of all things, something I've certainly not seen before, which is a Mars rover wheel, 3D printed, with a very interesting structure to the spokes of that. I don't know if we can get in on the end of that, just to show the spiral structure of the spokes, which is interesting. So there we have it, some fascinating additive manufacturing technology from Swansea. We are here on the CAVU Aerospace stand, and we're taking a look at some advanced solar cell technology. So this particular device here, which in terms of technical specification, two key criteria or two key benefits for space applications are the efficiency and also the weight reduction. We are on the Printech stand, and I'm talking to Albert, and we are looking at circuitry for space applications. And in particular, we're interested in the substrate material and the kind of manufacturing processes to survive the rigors of space. So to make sure satellites are functioning correctly and efficiently for as long as possible, all about durability. So over to Albert, tell us a little bit about the space environment and how your material technologies and processes help satellites function efficiently in those environments.
So, this material is a modified hydrocarbon, so plastic, and we use it because it has low loss, and we know it works down to really cold temperatures. Being in space, being minus, I can't think of the kelvins, but very, very cold. And we know that it works. This is the reason we use it. It's gone all the way around it. And see the mission up there, capstone mission. It's as far out as we've gone, orbiting the moon. And we know it works well. That's why we choose it.
And so we're now on the Amphenol stand, and we're looking at some connector and PCB technology specifically designed for space applications. So we're talking lightweight, ultra-reliable, hermetic sealing, space-specific materials, zero outgassing, that type of thing. So we'll look at a couple of these. First one we're going to have a look at is Raptor, which is a power connector. So you can see there the male and female contacts in there. That's got an interesting connecting mechanism. First of all, it's keyed. So I've just got to get the key way sorted out. So it pushes together. Then we've got a ratchet connection there. And the interesting thing here is the red band around the connector there, so that you can now determine that that connector is made, and then unwinds like so and pulls apart. So it's nice, lightweight. There's no real mass to that. And once again, designed for reliability in satellite applications. And then if we take a look down here, this is from Amphenol Ltd. This is an example of a high technology printed circuit board for aerospace type applications. So a lovely example there. So if we move to the next cabinet along, I just wanted to have a quick look here. This is from Amphenol Martech, which is a company they acquired a little while ago. It's a company I know pretty well. been to their site because they're based just up the road, about 15 miles from our office. And these are hermetic glass to metal seals. So this is where you need to be completely impervious to gas leakage past the pins from a vacuum or pressure into the actual spacecraft itself. So very high technology, high performance metal to glass seals. And then finally, we'll just have a look here at hermetic packaging options. Again, this would be to seal a circuit into its package. There's typically some sort of semiconductor-based device or semiconductor-based circuit. And there we are. Several examples of space technology, all focused on lightweighting, high reliability, high durability. Okay, on the microchip stand, and we are looking at microprocessors and semiconductor devices. And what we're looking at here in this particular demo is a microprocessor, the core of that board. The newsworthy bit really for Space-Comm is the gold color of that particular device, and what that means is that it is radiation hardened. Obviously, semiconductors in space are going to be subject to high levels of radiation and need to be protected from that. And so this is a rad-hard device to survive in those space applications. And we're on the ClearSpace stand. It's a company we've written about in SE Magazine in the past. And this is all about sustainability in space. It's about refueling, it's about maintenance in orbit, and it's also about capturing space debris to be able to bring back to Earth for recycling. So this is an interesting demonstration we have here. We have kind of a mock-up of some space hardware, and then this particular unit here, where there's a camera-based device there. And this is essentially researching how the satellites will be identified and oriented and captured in space. So what they're doing is they're creating synthetic models in CAD to train what will be the grippers to clasp hold of a satellite. Because all of the satellites are effectively random, they're unlikely to have fiducial marks or anything like that. What they're looking for are edges and components that they can essentially visually latch onto. In addition to synthetic images based on CAD systems, they're also producing mock-ups and using the manufacturer's data to look at different materials, so for different surface finishes, which will be governing kind of reflections in space. Then if we come around to the display, we can see, obviously the lighting is not ideal here. So we can see here, this is the image on the left-hand side of the actual model. And then on the right-hand side, you can see how the camera, just wait that coming to focus, the camera is latching on to edges and features, starting to train the system in terms of identifying that object in space. So in the future, that is how space hardware will be refueled, maintained, serviced, and then potentially brought back to Earth in an automated, computer-controlled fashion. This time we're looking at another demonstration, which is a robotic arm, which will be the type of device that will be latching on to satellites in space so that they can be held for refueling, maintenance, repair, and potential recovery. So if we come around and have a look here, this is a mock-up of the type of attachment ring that the other spacecraft will see. That's going to have camera-based systems on looking at fiducial marks on the capture ring, and also then specific gripper attachments, so that as the spacecraft comes into position, it can then identify accurately and grab hold of the ring on the other spacecraft, so that it can pull it in and capture it for its refueling, maintenance, etc. We're on the Markforged stand today. This is additive manufacturing, which is a specific interest of mine. And this is super advanced technology that we're looking at here. So, for example, this particular component here is fiber reinforced. But what makes this really special is that this is continuous fiber reinforced. So if we just take a look at the machine here, you can see there a reel of continuous carbon filament. And there's a secondary nozzle in the print head, which is laying down a continuous fiber reinforcement, which is then bonded in between the polymer layers. The kind of strength characteristics or rigidity characteristics can be controlled, whether it's longitudinal, cross weave, or 45 degrees. Moving on from the polymer materials, we then come on to the metal printing, which is equally as fascinating. So if we look at powder-based 3D print, there you can see a filtration device for a medical product. Very, very fine detail. There we're looking at a metal part which has been manufactured using a filament-based machine. So here a metal powder is captured within essentially a kind of wax-like filament. It's printed using the sort of conventional filament printing techniques, and then it's post-processed. So it's cleaned and would then go into a sintering oven. So it'd be manufactured slightly oversized so that it prints to the final dimensions. So now you've got the option of traditional polymer filament print, continuous fiber reinforcement, powder-based metal, and filament-based metal, covering all the options. You can then try, or you can then end up with sort of hybridized assemblies, where aspects of the design can be metal printed, hybridized with polymer printed parts as well. So this is real high-end additive manufacturing technology that we're observing right here, right now. And this is production level technology in additive production. I'm on the Camberley rubber stand, and we have a fascinating example of space-related material technology and geometric design solutions for this particular part here, which is part of a propulsion system. It's part of the fuel system, so this would be found inside a fuel canister or fuel reserve. Inside is going to be the propellant, which is hydrazine, which is a very aggressive chemistry to be dealt with. So the chemical construction of this particular diaphragm has been engineered specifically for that chemistry. It's been tested independently and is good for 15 years of operation in space environment. The way this works is that an actuator within the system would be essentially compressing this diaphragm and forcing the fuel into the propulsion system. And the way it's been designed is that these support ribs down here and these cutouts here mean that that diaphragm will fold in a how can we put it, a known manner. So over a 15-year period, it needs to retain that propellant safely and then form itself accurately until the fuel is exhausted. And all of that is about the material science in the base elastomer here, and also the design of, for example, the clamping ring, the support ribs, and the fold points here. So, excellent example of a durable, reliable, repeatable, high-performance engineered solution in a very, very demanding space-based application. I'm on the Solsta stand with Matt, and what we're doing is taking a look at the aerospace-related technologies that Solsta is offering at the moment. And so I'm going to ask Matt just to literally step us through the display case here, just to give us an indication of the types of technologies that are available in space applications, and what the kind of fundamental benefits of those technologies are. So Matt, if you can just literally walk us around the cabinet, that'd be brilliant.
We're Solsta, we're a value-added distributor servicing various markets, but here we're all about high rail and space applications.
We are showing some of the product lines that we have here. We have flexible temperature devices from Minco. We have optical transceivers from Smiths Interconnect that are rated, they're rad-hard and rated for space use. We have silicon sensing products for detecting acceleration, orientation, and so on, where you're at, where maybe you don't have a GPS signal, so you can use it for positioning. We have transformer products from Incor, products from Accelitas for photon detection, things like PIR sensors. We have relays which are used for switching high frequency feeds, rotary relays, panoramic, high reliability, high voltage capacitors, and that's what we got here.
Okay, I'm on the Olsen stand today and I'm talking with Piers, and what we're looking at is actuation technology for aerospace applications. We're looking at a sustainability angle in terms of space, weight, energy efficiency, and overall technical performance. So over to Piers to explain the sort of technical speciality of this actuator compared with typical ball screw actuators, hydraulic or pneumatic systems. Over to you, Piers.
Good afternoon, thanks very much. Piers from Olsen Actuators. We design and manufacture these precision ground planetary roller screws, and the advantage of the planetary roller screw is that you can develop 6 times the force in the same space envelope as a ball screw, whilst giving about 30 times extended life. Therefore, we can reduce the size of the mechanism to reduce weight and still offer you a higher loads and a longer life. So that's obviously sustainable because you're using less fuel because the aircraft weighs less. And also the energy consumption is far lower than its pneumatic or hydraulic counterparts. So it'll consume 5 times less energy than a hydraulic when it's running, and actually no energy when it's not running, or 11 times less energy than an equivalent pneumatic air cylinder. So obviously less energy is better. Plus there's no mineral oils to dispose of and all the associated maintenance, the regime that you have with those legacy aerospace systems. So yeah, long life, low maintenance, low energy.
Okay. Can you tell us a little bit about the drive, the sort of propulsion system? You were mentioning servo motors with encoder setups, and what sort of level of precision you can get to in terms of actuation?
Sure. So, depending on the shape and size of these roller screws, all different shapes and sizes depending on the loads, we would then, fit that with, drive this mechanism, use it with a motor. Might be a permanent magnet or a brushless DC, BLDC. This is actually a thin gap, space rated. We fit that to the roller screw mechanism and some bearings, and then we'd package that with an encoder. The encoder has an absolute revolutional accuracy of about 21 bits, so just over 2 million pulses per revolution. So 2 million divided by the lead of 2 millimeters gives you about just under a micron accuracy as standard. Yep. And then obviously we could use a gearbox to improve that accuracy for mirror alignment and photonics applications, laser communications, and so on.
Yep. You mentioned some applications there. Can you give us a sort of range of applications that these would be used for, from kind of big to small?
Yeah. So the rotary actuator, which would be packaged with usually a zero backlash gearbox, epicyclic gearbox, or a strain wave gearbox, can be used for solar array deployment assemblies. It could also be for positioning gimbals for, laser communication, cameras, RF communications and listening devices. One of the main applications for us down here with this actuator on the patented design, that one there, that's actually thrust vector control, so TVC for one of the UK's rocket manufacturers.
Okay.
So that thrust vector control obviously
Okay.
steers the rocket.
Yeah.
And it could be some quite big numbers. I mean, if you
Yes.
manage to get in on an American platform,
Yeah.
you know, there's a number of engines and each one
Yeah.
requires 2 actuators and then
Yeah,
you need the control electronics to control all this.
Right. Okay.
And this is a space-rated TRL-9,
Right.
low risk, fast delivery electronics
Okay.
to control these motors.
So you do full system supply in terms of actuator, gearbox, motors, encoders, and power delivery and control.
Quite happy to supply you the components if you want to make the assembly yourself, or we can do the design and the assembly for you. Because we have a team of engineering people and designers, senior guys, clever. So yeah, whatever you need, when push comes to shove, we can help you.
Excellent. Thank you very much, Piers.
Right, thanks a lot.
Excellent summary.
Thank you.
Thank you.